Welcome to the Hub Division Modular Railroad Signaling Testbed. My name is Eric Whitney, and I'll be your guide through this demonstration. Let's start with an overview of what this testbed is and how it relates to the Hub Modular Group's layout. The testbed shown here represents a combination of 14 active and passive modules. Active modules are ones which contain an active signaling node, which is CMRI in this case, whereas passive nodes contain no active signaling components. The only thing a passive module needs to have is the current Hub Division module wiring harness. We built the testbed to represent all of the different signaling scenarios that we use on our modular layouts. The signal aspects chosen are based on NORAC rules, and these have been extensively covered in previous Hub Clinic. In order to develop, debug, and demonstrate the signaling system, we built this testbed to create a tabletop representation of a modular layout. The circuit boards you see on the face of the testboard have signal heads, turnout indicators, and block occupancy detectors, which represent all of the active elements of our signaling system. Later on, we'll show the backside of this display, which has all the pieces of the signaling system that are typically installed underneath the module. This current version of the testbed is using CMRI nodes as mentioned earlier. However, we can replace CMRI nodes with LCC nodes to demonstrate how LCC can also be used for signaling our modular railroad. This is a topic for future demonstrations, so stay tuned. In addition to what you see here, there's a computer attached to the testbed via a USB cable, and that is how the dispatcher's panel is connected to the layout. This panel was created using the CAT software by Rodney Black. Both CATS and JMRI are free open source software packages available for Windows, Mac, and Linux systems. During the initial development of the Hub Modular Railroad Signaling System, we found that it was often difficult to diagnose and fix problems between the hardware and the software, especially since the layout changes for every train show and debugging issues during a show can be difficult and stressful. This testbed uses the same software that runs on a show layout, so any problems we fix using the testbed apply to the actual modules. Also, as part of this testbed development that we're not going to show in this video, is a collection of scripts and templates we've developed that allow for any show to be automatically configured from a list of participating modules. As we roll this out, there will be additional presentations to describe these details. This presentation is going to take you through a very straightforward case of two trains running in opposite directions. One train wants to go on the main line left to right, and the other train is waiting on the siding to go from right to left. Since the testbed doesn't actually have a train on it, train movement is shown by LEDs, which represent block occupancy. As the trains progress, we'll show both the testbed system and its LEDs along with the CATS panel that is communicating with the testbed and shows how each action is indicated. We are running this demonstration using ABS signaling, which is the simplest type of train control. ABS signaling does not require a dispatcher and is probably the default mode we will run at train shows. CATS is more typically used for CTC, so when we want to run a modular layout using a dispatcher, the scripts we develop can be used to automatically generate a CTC panel. This testbed will be used to debug and test this configuration, and we will present CTC at a future meeting or video. Before we move a train, let's look at the testbed in detail and see what's going on from each of the 14 modules. From this view, we can see all of the modules, 3 active and 4 passive on the top, and 3 active and 4 passive on the bottom. The numerical displays you see in the upper left corner of the testbed are power supply modules. This is the module power supply design I wrote about in my Hub Headlights Electronics Notebook column a few years ago. I know it's difficult to see all the detail from this viewpoint, so we'll zoom in on each module one at a time, but if you follow the white lines and see where there's an LED on each line, those show you where the track goes. It's a single track on the first 3 module in the upper left corner, and the first module on the lower left. Everywhere else, it's double track. For each track segment, the LEDs indicate red for occupied and green for unoccupied. There are only 2 types of signal heads used, a single-headed dwarf and a double-headed mast. Each signal is facing the direction of the train it's supposed to control, which you can tell by the white squares on the base of each signal. I should note that if you see a 2-headed signal that is indicating red over nothing, the lower head is supposed to be a flashing yellow. I had a bug in the signal definitions when we filmed this, which has been subsequently fixed. We have block occupancy and we have signals. The last element is the turnout indications. If you look closely at the active modules, you will see a white X. If there's a turnout there, you will see an LED mounted in one or more corners of the X. These LEDs indicate green if the turnout is normal or closed, and red if the turnout is reversed or thrown. CATS uses the terminology from JMRI, closed or thrown, which can be a little confusing, but you'll get used to it. Finally, you'll see 4 wire jumpers between the modules. Each jumper has red, black, yellow, and green wires. These represent the wires in the hub module wiring harness that pass along the occupancy information from one module to the next. However, the jumper colors don't match the ones on the wiring harness. Let's zoom in to each module, starting with the passive corner in the upper left. The only track indicated here is the arc from the lower left to upper right, and the LED is green, indicating that the block is not occupied. This LED receives its occupancy indication from one of the adjacent modules over those jumpers I just described. Remember, there's no active signaling circuits on a passive module. When we get to the CATS panel associated with this test bed, you won't see a distinction between the curved or straight modules. This is a physical characteristic that gets linearized when the panel is made. The next module is our first active module. This is a single track module with only the upper track. The signals are showing yellow over green, which indicates medium speed. There is no turnouts and the blocks are all showing green. I'd like to point out that each active module can have multiple blocks representing different track segments. The block definitions have been covered in previous clinics on modular signaling, and more information on this will be coming out in an upcoming hub module specification update. This next module is another single track passive module, but this time the track segment is straight. There's only one LED which gets its occupancy information from the adjacent module. The next active module is an OS left module, so it is a single track coming in from the left, and then the turnout provides a path to either of the two tracks on the right. You'll see the two-headed signals on the top and the dwarf on the bottom. All of the block's LEDs are green, and if you look carefully at the green LED that is the third one from the upper left, it shows green, indicating that the turnout is closed or normal. The LED in the center of the X will show the occupancy of the diverging route of the turnout, which is off now because the turnout is normal. The next module is passive double track. Both LEDs show green, and each gets their occupancy information from the opposite neighbor. This is how the occupancy information is propagated on the hub layout, so that behavior has been mimicked here. The next module is an active crossover. As I mentioned before, the second signal from the bottom should be showing red over flashing yellow. In this case, the turnout can direct trains either straight or cross from upper right to lower left or vice versa. If you look carefully, there's two LEDs at the corner of the X, and both are green, indicating that the turnout is closed or normal. The last module on the top row is a passive double track corner. Here, the LEDs are mounted on the arcs, and both are green. The next module is just below the previous one and is identical except for its orientation. Moving around the corner to the next active module, this is a double track module with signals but no turnout. You can tell this because there's no LEDs on the corners of the X in the middle. Proceeding to the left, there's another double track passive module. And the next active module is another crossover, but in the opposite direction as the previous one. Note there are two LEDs at the corner of the X and are a mirror image of the other crossover. In this case, it's the top signal that should be red over flashing yellow. Before heading in to our last active module, there's another passive double track. And the last active module is another OS, this time OS right. There's double tracks on the right, but only a single track on the left. Turnout is normal or closed, and the diverging route of the turnout is not occupied, nor are any other blocks. The last module on the bottom left is a single track corner module, and that completes our trip around the layout. Zooming back out, we can see the 14 modules, and hopefully it's a little bit clearer what's going on. I designed only 2 circuit boards to make all these combinations work, so it can be a little difficult to see what's going on at first glance. I thought about printing a cover plate over each circuit board that would let the LEDs and signals show through against a plain black background. This might make it easier going forward. Now let's look at a train meet with ABS signaling. Train T1 is sitting on the main and wants to go to the right. Train T2 is sitting on the siding and wants to go to the left. The dwarf signal indicates halt because the turnout is closed or normal. The main line signal indicates proceed because its route is clear. Note the opposing signal on the main indicates halt. Remember, ABS has its shortcomings in these situations, and there would likely be a timetable or train order that would likely govern the movement of trains. The test bed shows train T1 with a red LED at the left of the display. Train T2 is shown by the 2 LEDs in the upper right. You can see here how the occupancy is passed from the adjacent modules. Train T1's occupancy is being passed from the left, while Train 2's occupancy is being passed from the right. The turnout is clear, and the signals match the panel. At this point, we're ready to move Train T1. Watch the CATS panel as Train T1 occupies the blocks in this module and proceeds forward. CATS uses the occupancy information to follow the train movement and update the display. In this example, the only thing that indicates train direction is the order in which the blocks are occupied as the train moves. CATS also updates the signals based on the ABS signaling rules. It can be a little tricky keeping track of which switches set which blocks. The lower row of push buttons control the lower track occupancy, and the upper row of push buttons control the upper track occupancy. But there's also a pair of buttons in the middle of each row that were put in for future use as local turnout control, but these are not used in this particular configuration. The turnout controllers I'm using are the MRCS integrated turnout controllers I wrote about in one of my recent columns. These ITCs implement local control, turnout locking, and status LEDs, which I added to each of the 4 turnouts on the testbed. For further information, check out my headlight column or refer to the Modular Control Systems website. With train 1 out of the way, the turnout is thrown and train 2 proceeds to the main. As with train 1, CATS follows the train movements as it goes from block to the left. You probably noticed that the blocks on the testbed are unrealistically short. This is because I wanted to be able to keep the testbed small enough to fit on a tabletop. It should be clear that in order to prevent CATS from getting confused, the train must be fully equipped with resistive wheel sets to make sure the block occupancy detectors don't clear in the middle of a train. This could confuse CATS into thinking there are more trains than there actually are. We can simulate this condition on the testbed by not pressing the right buttons. And now for a brief tour behind the testbed to take a look at the components that would typically be out of sight underneath each module. As I mentioned before, this version of the testbed uses CMRI. Each CMRI node is configured to handle the required input and output control lines needed, and each node communicates with the next via the same RJ45 network cables we use on the modular layout. Since the current hub layout has a mixture of Bruce Chubb S-Mini boards and MRC CP nodes, we use both types of boards on the testbed so that we can sort out the issues we've had between the two. When it comes time to convert the testbed to LCC, all we have to do is disconnect the I/O lines, remove the CMRI nodes, and cable in the LCC nodes. The actual conversion is a bit more complicated than that, but that's a topic for another day. One major difference between modular signaling with CMRI and LCC is that with the RR circuit signal LCC nodes, ABS can be configured to run without any host computer attached. Whereas with CMRI, a host computer is required to be up and running during the show. Both systems use JMRI and CATS, however, configuring CATS to work with LCC is still a work in progress. That's all we have for now. Thank you for watching, and I hope you found this video interesting. Stay tuned for future videos about modular railroad signaling. Thank you.